Well, hi, welcome back. In this particular video, I'm going to show you how to derive the equation for the period of a simple pendulum. And you may not have dealt with a simple pendulum before. I'll describe in a few minutes what that is, what that looks like. But I want to refresh your memory of something you should have seen earlier about just a simple oscillator, which is a more familiar mechanical setup where you just have a mass on the end of a spring. A lot of times it's set up where the mass oscillates vertically hanging from a spring. You could also set it up where the spring mass system is kind of a horizontal thing. So there's different ways to set it up, but regardless of how it's set up, you arrive at a description of the motion that takes the form of what's called a differential equation. It's an equation that includes some terms that have derivatives. And for this particular situation, the differential equation looked like this. Here's where the derivative comes in. That's actually a clever form of acceleration, the second derivative of position with respect to time. And on the other side of the equation are the physical parameters that make up the oscillator, in this case the spring constant divided by the mass that's attached to it. And then here is the position that that oscillator is in. So what this means is, depending on the position where your oscillator is located, like where in the cycle it is, this way or this way, it determines what the acceleration is. It kind of makes sense. If the spring is most stretched out, in other words, you have the highest displacement from your equilibrium position, that's when you have the greatest pull from your spring and therefore the greatest acceleration. So this was derived in an earlier segment that I made. But it's important because you're going to see something later in this video that for the simple pendulum that looks awfully similar to that. And so that's why I wanted to refresh your memory about this. This equation also leads to a description of the period of the oscillator. And the period of the oscillator is determined only by the physical parameters that it's made from, which in this case is the mass of the object and the spring constant for the spring on which it's attached. So 2 pi radical m over k is how we describe the period of such an oscillator. So now let's look at what a simple pendulum is and how the equation for its motion is very, very similar to this one. So simple pendulum, and there are different kinds of pendula. The ones we'll deal with in this course are the simple pendulum, and then we'll follow that up with what's called a physical pendulum. There's also something called a torsion pendulum, but it's a little beyond the scope of what we're going to do here. So the simplest way to describe this is actually just through a little drawing. So imagine I take a string and I put a small little mass on it. Our string has a length of L, and the mass on the end of it is a mass of M. It's attached up here, maybe this is the ceiling or it's a ring stand or something like that. And so you see this back and forth motion, okay? Just like a pendulum on a grandfather clock or something like that, although that wouldn't be a simple pendulum because the mass that's on the end of that is a little too big to be considered simple. So simple means all the mass is concentrated at a small little point. So just a ball or something like that. So when we describe these kinds of things, we usually say, okay, we're going to pull back our little mass so that the string makes an angle of theta measured from vertical. And then we're going to let it go, and it's going to go back and forth like this. And in a simple pendulum, we ignore the effect of air resistance and drag and friction and things like that. So this thing, we can just imagine, will go on forever. So eventually it'll be over on this other side, making the same angle theta, and then back to here, back to here, back to here. So it's a nice periodic or cyclical kind of motion. So how are we going to describe this particular motion? Well, we're going to start with a form of Newton's law that works for rotating things. So that's not F equals ma, but the rotational analogy to that, which is torque equals I alpha. Okay, you should have seen that in your first study in rotation. So what's torquing this thing? What is it that's causing its motion? Well, the motion that it has is always tangential. Okay, you obviously can't stretch out the string or anything like that or make it shrink. And so all the motion is tangential. Now, what's causing that is a component of gravity. So here's what I'm going to do. Down here, I'm going to draw this mass, okay? Draw its forces. We got the string pulling up at an angle like that, so that's T. And we've got the weight, mg, down here. But the only force that's able to cause its motion tangentially is the tangential component of this. So we draw a little component like that, and we could also draw that down here. Again, we're just kind of breaking this into components. So the one that we have tangential here would be considered mg sine of theta, where again theta is measured from the vertical to the string direction. So that would be like this here would be theta. And that's why we're using the sine, because the component that we draw up here, we could also draw down here, okay? And it is opposite that angle theta, and so it would be found using the sine function. So now we're going to use this force here, that's our torquing force, to describe what the torque is on this particular pendulum. So remember, a torque is not just a force, it's a force multiplied by how far away from the rotation axis that force is applied. Well, in this case, the torque is applied right at the location of the mass, that's where the gravity is acting, and it's a distance L away. And so to describe the torque fully, we would use this component, mg sine theta, times L. Now, I'm going to insert a negative sign here, and here's why. If we have a theta that's measured, like in this case here, clockwise from vertical, do you see how the torquing force is applied counterclockwise? But if we're swinging up here and the theta is counterclockwise from vertical, then the torque is applied clockwise. So the torque is always the opposite direction of the actual displacement. Very similar to a spring. When we squish a spring leftward, it pushes back rightward, and when we pull it rightward, it pushes back leftward. That's why we're going to introduce a negative sign here on the torque. We refer to this as a restoring torque, or in the case of forces, it's known as a restoring force. So what are we going to put over here? Well, for a simple pendulum, it's very easy to describe the moment of inertia. Because it's a point mass, a distance L away from the rotation axis, it's a very simple mL squared. And then how are we going to describe what alpha is? Well, we're not going to change this into a linear version. We've done that other times before. We substitute the linear version of acceleration. This time we're going to write the angular acceleration as the second derivative of angular position with respect to time. Remember, acceleration is really defined as the second derivative of position with respect to time. So how do I write that symbol? For those of you, depending on where you are in calculus, this is still a little unfamiliar to you, but a second derivative is written this way. Okay? And its position, taking the derivative of position with respect to time, and that position has the symbol theta. That's the same theta that we used here, because that angular position is really describing how many radians we've swung this through. Okay? So notice a couple things nice here. The masses cancel out, and one of these L's here and one of these L's here will cancel out. And I'm going to do a very important thing that's going to seem kind of silly, but it's very critical to being able to describe this differential equation. I am going to replace the sine of theta with theta. So it's like I just got rid of sine, but there's a reason for that. This is known as the small angle approximation. It's used a lot, a little math trick that's used a lot. And it's only appropriate if the angles are small, less than maybe, say, 10 degrees or so. And if you're working in radians, which we are here, you can try this yourself on your calculator. If you take the sine of a small angle in radians, and you hit enter on your calculator, you will see that you'll get the same number back. So the sine of the angle and the angle itself are almost identical numbers. Okay, that's the only reason we can do this substitution. So I'm just going to rewrite this. I've canceled out a couple of things here, but I'm going to put in theta in place of sine of theta. So we get g theta, the negative sign on the front, equals L, and then the second derivative of theta with respect to time. Or rewriting just a little bit, d2 theta dt squared. I'm putting the second derivative alone on the left side, just that's where I want it. I'm not really changing anything here. And then a negative g over L theta. Now, why do I want it in that form? Well, it's because of what I reviewed with you at the beginning. Do you see that although these are not identical equations, the forms of the equations are identical? The only difference here is we're using angular position, theta, and up here we used regular old x, kind of a linear position. But everything else is in the same form. Okay? The significance of this means that the way to describe this simple pendulum is the same way we described a simple oscillator with a mass on a spring, which means we should be able to express a period for this as well. And all I'm going to do is I'm going to basically copy the period equation for the mass on the spring, but in place of the m's and the k's, I'm going to use what's down here, l's and g's in similar positions. So the period of a simple pendulum can be described as 2 pi radical L over G. Okay, again, very similar to this, just replacing m's and k's with what's in their same spots over here. All right, so you need to be able to derive this from what we call first principles, and that is Newton's second law. But everything else we did, except for this small angle approximation, is just using some tools that you've learned before. And I don't think this is a hard concept. It's just probably new. You haven't seen it before because, honestly, you've probably never needed it. So I'm going to stop here and let you work with this a little bit more. You can practice that to your heart's content as you want to, but hopefully it's something you can derive and get yourself down to this period equation as you need to. Thanks for watching.